Okay, so what I thought we would do is just start with just a review of some of the Calculus 1 material that I'm sure you haven't forgotten, but maybe just need a little bit of a refresher. All right, so number one, we've got a function. Start you off easy here. The derivative of f of x equals x squared minus 2x plus 3. Yeah, the only thing I guess tricky is remembering is this where I add one or subtract one, right? The derivative is where you, of course, just subtract one for the power. Well, you bring down the old power and make the new power 1 less. So it's just 2x, right? And then that'll just be minus 2. And then the derivative of a constant, 0. All right, but here's where you might remember a little bit, maybe. What's the derivative represent?
Slope of the tangent.
Slope of the tangent, okay. Yeah, if I plug in x to be 1, x to be 1 there, that would give me the slope of the tangent at 1. If I plug in x to be negative 3, it would give me the slope at negative 3, so good. It's also a rate of change. Isn't it? It's the rate of change of f, the rate of change with respect to x. Anything else? Those are the two main. You know, if this was specifically like this was a position function, the derivative represents the rate of change of the position, which is velocity. So you can get different measurements out of it. So, all right, number 2, f prime. If we've got f of x equals x cubed times cosine of x. Yeah, like I was saying earlier, that your derivative, if you've got those 3 or 4 rules down pat, power rule, first one, this one, product rule, right? Chain rule, quotient rule. If you know those, pretty much you got the derivatives of the trig functions. You got derivatives whipped. Yeah, here, the easiest one to forget is the product rule, right? I tried to harp on that a little bit as you go through Calculus 1, but yeah, so the derivative here, you have to get the product rule. Different combinations. I think I've settled now into saying, well, let's do the derivative of the first one, 3x squared. But the thing is, you don't do the derivative yet of the cosine, right? You just kind of alternate. When you have a product, you have to alternate doing the derivative. So the second part would be x cubed. Then you do the derivative of the cosine, which is, what's the derivative of cosine? Negative sine of x, okay? And we could, make that a minus x cubed sine of x, but for the most part, that's what we got. All right. And then number 3, of course, is our old friend quotient rule, right? 2x plus 1 over 3x plus 2. And so we're going to roll out the old quotient rule there. Yeah, so how's the quotient rule go?
High.
Yeah, that's the way I remember it. Is you start with the low, then do the d of the high. So we go 3x plus 2 times then the derivative of the one on top, minus then high d low. So you do 2x plus 1 times the derivative of the low, which is 3, and then that all goes over what?
Square of what's below.
Square of what's below. No square. All right, so then we can clean it up. That would be 6x plus 4, distribute, or that minus 6x, oh, that's going to work out nicely. Minus 6x minus 3, because you got to distribute the minus and the 3. And then 3x plus 2 squared. Okay, so that's 1 over 3x plus 2 squared. All right. Right? Didn't even have to tell you, right? Okay, number 4. Okay, so this gives us another little notation. What does that mean, d dx? What does this mean? d dx, same thing, derivative. Yeah, that's just another, we got the little mark, means derivative, but this too means derivative, so this kind of specifies the derivative with respect to x. Now we're doing the derivative with respect to x of that. What rule kicks in there? That's chain rule, isn't it? How does chain rule work?
Outside. Inside.
Derivative of the outside times the derivative of the inside. Chain rule. So this is the outside, this is our inside. So we do the derivative of the outside tangent derivative,
Secant squared.
secant squared. Now what happens to the inside when we do the derivative of the outside?
Stays the same.
Inside stays the same. So we don't change the inside when we do the derivative of the outside, because we do the derivative of the inside separately. And so we do the derivative of the inside part, 2x plus 2. Yeah. And again, remember, you can't distribute this 2x plus 2 in here because it's tied in with the secant squared. Yeah. All right, question? We're good? All right, rolling along here. So find, okay. Find dy dx for 2xy squared plus x squared y equals 10. Yeah, and I phrase it that way, find dy over dx here, because there's another process or another technique that we use for this one, isn't it? We call it implicit differentiation. Yeah, since I can't explicitly say what y equals or f of x equals like here, this we have to do with implicit differentiation. It's the same but different, right? Way I usually think is you're going to ddx both sides. That's, I guess, technically you're doing that on this one, but yeah, you just take the derivative of each side separately here. Now again, to do the derivative on this side, we do have a product, don't we? Well, all right, so you got to do the product rule for both of those. Now, all right, so the derivative of 2x is 2, so the y squared is going to stay y squared. All right, but then if I reverse it, do the 2x times the derivative of y squared, what does that work out to be? The derivative with respect to x of y squared. Well, you got the power rule, 2y, but since I'm doing the derivative with respect to x and it's a y, I need y prime or dy over dx, yeah. Yeah, you can use y prime there if you want. But, it's kind of a chain rule. We don't know what y is in terms of x, right? So that's why we do what we do there. All right, then the same thing over here. Product rule, so derivative of x squared is 2x, the y stays the same. Then reverse that, you got x squared times the derivative of y. Well, it's 1, but it's a y, so I need to do dy over dx or y prime. Are we okay with that? Then on the right side, easy. Yeah, it's the derivative of constant, so that's still 0. Of course, you combine things, but we're trying to find dy over dx, so what do? Well, I've got these dy over dx terms, so I need those other terms to go to the other side, don't I? So this will be 4xy dy over dx plus x squared dy over dx. And then those go over by subtraction, so minus 2y squared minus 2xy. Then what? Well, now I can factor off the dy over dx and then divide off the other part. Remember all that? So you got to divide by the 4xy plus x squared. Okay? All right, what else we got? Well, okay. Yeah, we'll pull out the old definition of derivative from time to time just to help us get going on some other derivatives we've talked about along the way. the definition of derivative, I mean, I'm not going to make you do the definition of derivative for those that we know the rule for now, but just a reminder, definition of derivative, f prime of x equals, well, it's a limit, right? Limit as h approaches 0, f of x plus h minus f of x over h. Remember those days? Yeah, but this is where it all comes from, because remember that's just a slope of a secant line, right? That's where that came from. It's the difference of the y's over difference of the x's. You know, the x's, the difference of them is just h. So that's a slope of a secant line, and then you do the h approaches 0, you come up with the tangent line. And so, anyway, good stuff. All right, number 7. Evaluate the integral. -3 to 0, x squared minus 2x minus 8 dx. All right, so yeah, this is where you have to remember this is an antiderivative, so we do the opposite of derivative, right? Where you go raise it to a power and divide by the new power, make it 1/3, whatever. Antiderivative, right? And this is a minus, so I can just do the antiderivative of that. That's just going to be x squared, isn't it? Because you'll divide 2 by 2, and then that, what's the antiderivative of that? You add an x. Now, we don't have to add the plus c when we do the definite integral. If it's an indefinite integral, you need the plus c. But here, it's an indefinite, so it's just a matter of plugging in some numbers. First one, top one goes first, so plug in zeros, those will all be 0. Minus, then plug in the -3. -3 cubed is -27. Minus x squared, -3 squared would be 9. And then minus 3 times plus 24. Okay, so what is that? -9 minus 9 plus 24. I believe that's 18. No, 6. That's minus 18 plus 24 is 6. Okay. Yes? Okay. What does the integral represent, graphically speaking?
Area under the curve.
Area under the curve. Okay, that's our shorthand way of saying it. What curve? This is our curve right here, right? Y equals that.
Curve of the function.
So, yeah, if I graph y equals x squared minus 2x minus 8, I think I brought my calculator. I think I know what that looks like, but just to be sure. X squared minus 2x minus 8. Graph. Oh. Didn't like my square there. Okay. Yeah, that looks better. So, what area is it? Well, we say area under the curve, but this one works out. So we're going from x equals 0 to x equals -3, which I believe -3. This is real close to -2 right here. So -3 is on this side. So the area actually goes from here. So if I take that up, it's that area, and then this area, right? And this one worked out to be 6. But it's a net area, isn't it? Because this is positive and this is negative because it's below the x-axis. So the net result is we wind up with an area of 6, but it's a net area, this minus that, if you will. You know what I'm saying? Okay. And then just a couple more integrals. Number 8. A's got what? Integral a over x squared plus square root of x dx. Okay, so yeah, it's just basically a reminder that's an A. Just a reminder here, to do this one, I'm probably going to have to rewrite that as a times x to the -2, and then that would be what power? Square root is 1/2 power. And so now our integral of that, what about the a there? Well, with respect to x, the a is constant. And so it's just like having a number there. So that's just a number. And then, okay, so we, again, antiderivative, so we add 1. So the a just kind of comes along for the ride. We add 1, we get -1, right? To the power. So we divide by -1 there. Same thing here, we add 1 to the 1/2, 1/2 plus 1, 3/2. And then what's the number in front here? It's reciprocal, right? 2/3. And then this is an indefinite one, so on those, yeah, we're still required to put the plus c. So minus a, x to minus 1 plus 2/3, x to 3/2 plus c, and you can write, you could write that minus a over x, I guess, but that's okay. Is that okay? Question or concern? And then, one more, and then we'll do some other stuff. What about that? Any ideas? Well, the complication on integrals comes pretty quickly. There's not a product rule for integrals, unfortunately. Antiderivatives, there's not a product rule. There's a power rule for antiderivatives, but not a product rule or quotient rule. I guess not really even a chain rule, but what other tool do we have for this? Remember? For integrals? You can't do it directly because the thing is, these were direct antiderivatives because it was plus or minuses, same way you just do the antiderivatives. But when it's times, that complicates things quite a bit. And so when you look, the first thing you always look for, because we're going to learn other techniques, but the first thing you always look for on integrals is U substitution. Remember that? U substitution? U sub, I call it, or just substitution. But yeah, we assign the variable U to part of this, and usually if you got parentheses, that's a strong hint as to what assignment for U should be. So yeah, let U be the x squared. Then you also need the du, which that's just the derivative of that, which is 2x times dx. And the way I did it is go ahead and solve this for dx, so divide by 2x. And then make those substitutions. We substitute x squared, we're going to leave 6x here. So it'll be sine of u, and then dx is du over 2x. So yeah, just make those substitutions there. Because this works nicely, because now we got some reducing here. The x's cancel out. Of course, this 2 and the 3, 2 and the 6 reduces to 3. Yeah. This works because now we've gone from a product, something x times something x, to now it's just one expression with u, sine of u, 3 sine of u. And that's just a simple antiderivative. What's the antiderivative of sine? The antiderivative.
Negative cosine.
Negative cosine, yeah. Yeah, remember, the derivative of sine is the cosine, the antiderivative of sine is negative the cosine. And on the substitution, go back to the x, so back substitute the u back in for u is x squared. So. Okay, and there's of course more complicated versions of that, but hopefully that'll spur some memories. Okay? All right. So that's that. Okay, one thing that we did not cover in Calculus 1 was a type of function called the exponential function. And so that's where I want us to go now, is to talk about the exponential functions and what ultimately what, well, we'll get into the derivative. First of all, what do we mean by an exponential function? And in general, basic exponential function is just some number to a power, right? We did not talk about where the power was the variable. We talked about x to a power rule, but power rule is not going to work on this because x is the power, and it's not a power rule. Unfortunately, that'd be neat if it was, but it's not, okay? Unfortunately, it is not. Now, we can get a little bit of information out of the definition, and that's why I mentioned earlier about recall what the definition of derivative is. And so the derivative here, definition-wise, here's what this tells us. We have the limit as h approaches 0, well, it's f of x plus h minus f of x over h. And so that, if you plug in x plus h for x, you have the limit as h approaches 0. It would be a to the x plus h minus a to the x over h. and that's, we did not do limits of that sort either. It's complicated, I guess, but not too bad. But here's what we can do. Actually, it turns out a to the x plus h we can write this way. See what I did there? I just wrote a to the x plus h times a to the x as a to the x times a to the h. Isn't that? Usually we go this way with it where we add the exponents, but we can break it back up if we want to. And the reason you do that is because notice then I've got a factor of a to the x. So I can factor that off. So if I factor a to the x off, that leaves me a to the h and then minus 1. Kind of a placeholder there. And then the good news is h is going to 0, so that a to the x is a constant, and so I can bring it out outside of the limit because this is not affected by the h going to 0, so I can just bring it out. Okay. Now, we'll say more about this later, but the nice thing about this is this derivative turns out to be that. And so notice one thing about the derivative of a to the x is in part of the derivative. So the derivative of a to the x, or a number to the x power, part of it is itself. That's interesting because we've never had that happen. But part of the derivative of a to the x is a to the x. Now this other part, what I'll say about that is that just turns out to be a constant, a number. And after we do something more in just a second, later, I'll say more about that, what that is. But basically, the derivative of a to the x is itself times a constant. That's what we can that's what we'll say right now, okay? And it varies, like for, whoops, f of x equals 2 to the x, the derivative, and you can do it, you know, plug in the 2 here, 2 to the h, and do a table. Remember doing those? I don't make you do those, but we did it that way. But what we can say right now is it's 2 to the x times a constant, and it turns out that constant's about approximately 0.69. You know, there's a more precise one, but value for that. But But yeah, if you did like a table, put a 2 in there and then do the limit as h, you get about 0.69 approximately. For 3, it's about 1.10. But there is good news on that. There is a more specific value for that, and we'll talk about that in just a second. Okay, now here's some really good news. If it turns out there's this base, A here is the base, so depending on your base, that determines your constant there. But if the base is base E, the number E, have you ever worked with that much? Base E? We do a little bit of that in some of the algebra, but E is just, it's a constant like pi, right? 2.71828. It's, it looks like the way it starts is it just repeats 1828, but the next one's 459. So it's like pi, it's an irrational number. It doesn't repeat or terminate. But what I was going to say was, if it turns out that this number, actually the definition, or one way to define it, is E is the number for which that, we had, what was it, f prime of x was raised to a to the x times limit h approaches 0, a to the h minus 1 over h. One way to define E is the base that makes this 1. This limit of a to the h minus 1 makes that value 1. So in other words, E, the limit as h approaches 0 of e to the h minus 1 over h is 1. So this part of my exponential derivative, that part is 1. So do you notice what that means? So if you've got f of x equals e to the x, the derivative is, well, it's e to the x times this limit of e to the h minus 1, but e to the h minus 1 over h is 1. If f of x equals e to the x, the derivative is e to the x. E to the x is its own derivative. Pretty interesting little function, because what other function can you say that about? I don't think there's any. E to the x is its own derivative. So it's pretty nice. So they have some in this section here. Okay, so what if I've got, so what about f of x equals x cubed times e to the x? Well, the derivative of that, well, you got the product rule. 3x squared times e to the x. And then reverse that, so we've got x cubed times the derivative of e to the x, but the derivative of e to the x is e to the x. So run into stuff like that. What about f of x equals e to the 5x squared? So what if we have, what if we don't have the power being x? In this case, it's 5x squared. E to the 5x squared. Well, what rule is going to kick in there? Chain rule. It's a chain rule. The e to the 5x squared, it's not the most obvious chain rule, I guess, because you don't have the inside and outside, obviously, going there, but the power is the inside. The base is the outside. So, with that in mind, what's the derivative of the outside? Well, it's e to a power. e to a power, the derivative is e to the power, yeah. But since it's a chain rule, I also have to do the derivative of the power, right? So what would that be? Derivative of 5x squared, 10x. With me there? So if you got something e to a power other than just x, it's e to that power times the derivative of the power, because it's a chain rule. Yeah, this one had some interesting things that happened. Let me hit it too. Okay, so we've got y equals e to the minus w over e to the w plus 1. Quotient rule, of course, is what we're going to do. So low d high minus high d low over low squared. So low e to the w plus 1 times the derivative of e to the minus w. Well, that's kind of like the one we just did. E to the minus w, well, the derivative is itself. But since the top is not just w, I also have to do the derivative of the power. So that would be, what would be the derivative of the power? Negative 1. So it's e to the w plus 1 times e to the minus w times negative 1. Switch those up. So that's low d high minus high, e to the minus w times the low, okay? So what's the derivative of the low? Derivative of e to the w is e to the w itself. And then the derivative of 1 is 0, so it's just w. And then over low squared. I think this one is just a matter of, yeah, a lot of stuff in these to get down to the answer. You have to really know some algebra stuff, so might have to review some things along the way. But here, that's just minus e to the minus w. So I just need to distribute that. And when I do that, okay, so it's minus, I've got minus e to the minus w times e to the w. And so what do we get there? E to the minus w times e to the w.
E to the 0.
Yeah, remember that's where we just kind of did that in reverse. That's where you add those exponents. So you wind up with minus e to the 0, which is minus 1. Anything to the 0 power is 1. So that times that's 1, and then that times that, of course, is just minus e to the minus w. And then we have the same sort of thing here, don't we? That's e to the 0, which is 1. And then, lo and behold, oh, it doesn't cancel, it's minus 2. So there's probably some other things we can do, but you get the idea. All right. Now we said we're going to do derivatives of exponentials, but hey, let's throw in an integral here too. And the good thing about an integral of e to the x, well, I mean, the good thing about this one is it's easy. Since the derivative of e to the x is e to the x, the integral of e to the x dx would be e to the x plus c, yeah. I mean, if you have a power other than x, of course you've got to think through that. This one we can do with the substitution, can't we? Just I like to call these simple substitution. They'll come up all the time in this course, so be ready. But yeah, e to the 2x. To get this done, we just do a u substitution. U equals the power 2x, and then du would be the derivative of 2x, which is 2 times dx, and so divide by 2, and that's my dx. So we wind up with e to the u times du over 2. So that's why, you see, I call it kind of simple substitution, because really all it amounts to is we have a factor of a half there that we didn't have in the previous one. You see what I'm saying? Well, it's 1/2 e to the u. That's 1/2 e to the u, isn't it? Antiderivative. Let's see, and then just change back the u to 2x. Yes? Okay. Okay, now, let's talk about derivatives of logarithmic functions. And maybe a little rusty on the logarithmic functions, but just know, first of all, logarithmic functions are the inverse function of an exponential function. Yeah, if I've got log base a of x equals some number y, the reason it's called the inverse function is because that statement right there, that expression right there, equation, the exponential